Welcome to This Explainer. Today, we're diving straight into a dramatic, forensic countdown of history's most devastating engineering disasters. Using high-production CGI recreations, we're taking a deeply investigative, what-went-wrong approach to see exactly what happens when the world's most brilliant minds push technology to its absolute limit and the systems just shatter. All right, let's kick things off by looking at this staggering figure. We're talking over $2.3 billion. That's the combined minimum financial loss of just the 4 scientific blunders we're going to investigate today. But the true cost wasn't just cash. It was years of delayed research, thousands of hours of lost labor, and in the most tragic cases, actual human lives. So it begs the ultimate investigative question, right? How on earth did teams of the world's smartest engineers, backed by massive budgets and super rigorous testing, completely miss microscopic errors that brought down billion-dollar projects? Well, as you'll see in this explainer, these disasters almost never stem from isolated random glitches. It's usually the result of systemic, human, cognitive, and organizational breakdowns. So let's start the countdown. Number 4, the Hubble blur. A masterpiece aimed at the wrong target. Back in April 1990, the $1.5 billion Hubble Space Telescope finally launched. But excitement quickly turned to horror when engineers realized its first images were hopelessly flawed. Instead of the razor-sharp imaging they intended, the telescope returned pictures with a crisp core completely wrapped in fuzzy halos. This is what's called a spherical aberration. Basically, light striking different zones of the massive mirror was focusing at different distances, which completely ruined the contrast needed to observe really faint, distant objects out in space. And what makes this failure so incredibly frustrating is the crazy contrast in scale. You have a billion-dollar satellite, literally the size of a school bus, totally crippled by a truly microscopic error. The outer edge of the mirror was polished too flat by just 2.2 micrometers. To put that into perspective for you, that is roughly 1/50th the width of a single human hair. It's a flaw way too small to see or feel, yet it was large enough to effectively blind our greatest eye in the sky. Now, the crucial takeaway here is that nobody on the manufacturing floor was careless. Actually, scratch that. They executed their job with unbelievable precision. The problem? First, their testing instrument, the reflective null corrector, was flawed by about a millimeter. Because of that, the primary mirror was ground flawlessly, but to the exact wrong shape. It's like perfectly tracing a broken ruler. It wasn't until December 1993 that a shuttle crew had to actually fly up there and effectively fit the telescope with a giant set of corrective glasses. Number 3, Ariane 5, Flight 501, the dead code that blew up a rocket. Let's rewind to June 4th, 1996. The maiden flight of the European Space Agency's Ariane 5 ended in a $370 million fireball. Let's do a forensic second-by-second breakdown of this disaster, because the tension in mission control must have been unreal. At T plus 36.7 seconds, the backup inertial reference system processor just halts. Then, exactly 50 milliseconds later, the active unit does the exact same thing. Suddenly, the onboard computer has no healthy attitude source, it misinterprets diagnostic bit patterns as actual flight data, and it commands full nozzle deflection. At T plus 39 seconds, the rocket abruptly veers 90 degrees, and aerodynamic forces literally rip it apart at an altitude of 4 kilometers. So, what was the smoking gun for that terrifying chain of events? It was an active software routine attempting to cast a 64-bit floating point variable into a 16-bit signed integer. The thing is, the Ariane 5 accelerated way faster than its predecessor. This meant the horizontal velocity value quickly exceeded 32,767, which is the absolute maximum physical limit of a 16-bit signed integer. And boom, that triggered a fatal overflow. What's truly fascinating about this whole mess is that the code itself wasn't actually buggy. No, it had flown perfectly safely on the older Ariane 4 for a decade. But it was like an unwritten contract that no one bothered to renegotiate. The hidden physical assumptions of the software, basically that the rocket would only accelerate at a certain speed, changed from true to false without a single line of code ever being touched. Reusing software without revalidating the new flight envelope proved to be an absolutely catastrophic blind spot. Number 2. Mars Climate Orbiter, the $492 million metric mix-up. Jumping to September 1999, a $492 million mission was entirely lost. Think about this massive trajectory drop. The target altitude for the orbital insertion was 226 kilometers. Now, the absolute minimum survivable altitude before atmospheric friction and thermal stress would just incinerate the craft was 80 kilometers. But due to a doomed trajectory correction maneuver, the actual trajectory plummeted down to just 57 kilometers. It literally never had a chance. So how did navigation get it so horribly wrong? Believe it or not, the fatal data integrity issue came down to simple units. The spacecraft manufacturer, Lockheed Martin, was outputting thruster impulse data in imperial units, pound-force seconds. But NASA's Jet Propulsion Lab assumed the values were in metric units, Newton seconds. So they interpreted a value of 4.5 pound-force seconds as 4.5 Newton seconds, when it actually should have been 20.03. They underestimated the thrust force by a massive factor of 4.45. This brilliantly illustrates the Swiss cheese model of failure. A simple math error doesn't destroy a spacecraft all on its own unless multiple layers of defense fail simultaneously. First, the thruster geometry hid the error. Then, two different navigators actually noticed the trajectory drifting, but their warnings were completely dismissed due to poor communication. Add to that, the statistical analysis was totally inadequate, and a critical contingency maneuver was aborted simply because the team was understaffed. It was a compounding systems engineering failure through and through. Number 1. Therac 25. The perils of eliminating hardware interlocks. We've arrived at the most devastating software-related medical accident in history. Between 1985 and 1987, this radiation machine massively overdosed 6 people. To understand this absolute tragedy, we have to look at the dual-mode design of the linear accelerator. It had an electron mode, which used a low-energy beam for shallow tissues, and a photon, or X-ray mode, which fired a highly lethal 25 MeV beam that required a metal target to be safely placed in the beam's path to generate X-rays. Older models used physical, mechanical hardware interlocks to make absolutely sure this target was in place. But the Therac 25? They eliminated those hardware interlocks, relying entirely on software checks to handle the safety. The underlying coding flaw inside the Therac 25 was a ticking time bomb known as a race condition. If you aren't familiar, this is a concurrent programming error where a system's behavior depends entirely on the timing of uncontrollable events. In this case, it was something as simple as how fast a human operator types on a computer keyboard. And here is the horrific sequence that software flaw allowed. First, a software bit flag was programmed to increment rather than simply being set to a fixed non-zero value. Because of this, an integer overflow occurred, which essentially rolled the safety check back to 0. This completely tricked the machine into thinking it was safe to fire. Ultimately, the massive 25 MeV electron beam fired directly into the patient without the protective X-ray target in place, delivering 100 times the intended dose of radiation. The human element, epistemic vulnerabilities in systems engineering. Okay, so beyond the bad code and the microscopic measurement errors, we have to take a hard look at the root cause of all this, the human element. The core psychological trap at play here is confirmation bias. In the Therac 25 tragedy, the engineers suffered from what experts call expert immunity. They fundamentally believed that their sophisticated, software-controlled machine simply could not malfunction in that way. Because their pre-existing mental models told them the software was foolproof, they repeatedly dismissed operator warnings and initial reports of radiation injuries, only selecting the data that confirmed their own bias. To fortify quality control and prevent these devastating blind spots moving forward, organizations absolutely must apply these vital lessons. We have to verify reused software in its new environment, exactly as Ariane 5 taught us. We must implement diverse hardware-level redundancy, as Therac 25 tragically proved. We have to enforce incredibly strict data contracts across teams to avoid another Mars climate orbiter mix-up. And finally, we must rigorously investigate conflicting high-precision tests rather than just ignoring them to prevent another Hubble blur. Ultimately, as we've seen throughout this entire forensic countdown, our most expensive and tragic failures are not simply bad math or stray lines of code. No, they're human failures, failures of imagination, communication, and rigor. They are systemic failures driven by predictable cognitive biases that allow deadly errors to just slip right past our defenses. So, I want to leave you with this really provocative final thought. Look at the technology you trust every single day. Think about the invisible code running in our cars, our medical devices, our entire infrastructure. When we reuse old assumptions and start trusting our systems more than our own independent safety checks, what unseen disaster is currently waiting in the code we reuse today? Thank you so much for joining me for this explainer. And remember, keep questioning the systems around you.